Okay, hey everybody. If you're sticking with me from the previous video, welcome back. If you haven't, make sure you go back and watch 12.1. This is the second section in chapter 12. So a little more advanced, we're now talking about the differentiation of integrals. And so if you see here at the beginning, or just to preface, this is going to involve some partial derivatives and differentiating different functions. So a little good refresher maybe from like differential equations if you took that a few years ago. But basically, if we have a function with two different variables, so sometimes we have functions with x and y in it, and generally in real life, most functions are not just one variable. So we can have two functions of y, and if you see below, this would be only a function of y, even though x is in it. So it is kind of awkward, but if you notice here, this is only referring to y. So our definition 0.4, Leibniz's, sorry I butchered that, rule for differentiating an integral states that if I have some function with two variables and it has continuous functions as the bounds, then to differentiate f of y, I actually can take the derivative of h of y, also with the function of h of y comma y, and subtract the derivative of g of y times the function of g of y comma y, and then adding this integral we would evaluate. Because before, I can't evaluate this integral properly, so we actually have to use this rule. It'll make a lot more sense when I show you an example. Basically, this section is very cut and dry. So there's this rule, and it's basically a formula of how you go about solving this. So for example 0.2, if you notice, I have a function of y, and both my boundaries, in this case, one is not a variable, but treat it as a function. So like how we have up here g of y and h of y, this is g of y, and this is h of y. Just because technically we're considering one a function. And if you notice, our function is a function of x and y. So I'll just write that there, kind of labeling it for you guys to see. And they want us to find the derivative of f of y, which is already difficult because it's already an integral and not a derivative. So the solution would be, so like I said before, we have f of xy as our function of two variables. And then h of y, like I pointed out, is y squared. So then if we differentiate h prime of y, we get 2y. So you basically, any of the functions of just one variable, you differentiate it the way that you are used to. So these are probably self-explanatory. Same thing with 1 and 0. The one thing that I am going to point out here is you will have to take a partial derivative of f with respect to y, because they want f prime of y. We are only concerned with the y. So if you notice, we get 1 over x. If you recall, when we take a partial derivative, you treat so if x is the variable we don't care about, you treat that as a constant. So here, y over x, think of it as like y over a number. And that's why we ended up getting the 1 over x, because y would go to 1, and you're just left with 1 over x. So using our formula from definition 0.4, if you notice right here, we are going to put 2y times y over y squared, which is f of h of y comma y. So when they say f of h of y comma y, they are just telling you to plug h of y and y into our f of x function, or f of xy function, excuse me. So basically it's just plugging in the numbers, and you see our integral is now much easier for us to solve. Like, we know how to solve integrals in regards to one variable, and that's where the ln of x comes in. And then you would just plug in the variables the same way. So it still becomes a function of y just because of that. we'll actually go through a problem. I think it'll become more clear as to what's going on. So we're given this f of y. So we need to plug, let's pick out all of our functions right now. So f of xy is for sure yx squared dx. Okay, so we have a function of two variables, and then our h of y is y, and our g of y is 0, conveniently. So we are going to need the differentials of all of these, and this is the partial symbol, this little like weird backwards 6. So we want the partial of f, and we want it with respect to y. So that's why I have the partial of y symbol below. And like I said before, treat the x squared. So like this is a constant. Don't even think about it right now. All we think about is differentiating y. So if I take the derivative of y, that's literally just 1. And the x squared would stay like any other constant. So that's x squared. H prime of y. Here I'm going to, let's make this a little bit cleaner. I'm sorry. Yeah. There we go. Apologize for that. So h prime of y, we will also need that. We can just differentiate that like any other function. We'd get a 1. And then same thing with g prime of y. We actually got lucky here because it's just, differentiating 0. And these are the 4 parts that we will need to complete the formula. So Leibniz his formula, I'm going to write it out just because it is super long and we're going to want to remember it from above. So it states f prime of y can be found with h prime of y times f of h of y, comma y, minus g prime of y times f of g of y, comma y. And then we add it all to our integral of g of y to h of y of the partial of f of x y all over y dx. Okay, so now that we have our formula and we have all the pieces, we can evaluate. So I'm going to just write mine now below in a different color. So h prime of y, if you recall, was 1. I'll zoom out. So we have 1. And so when they say f of h of y, comma y, our f of xy, we remember, was yx squared. So we're just plugging in, that's x and that's y. We're plugging in h of y for x. So h of y is just y. So we'd have y squared. And we're plugging in y for y. So we would still have y there. And that would give us y cubed. So that's kind of the process that we go through. Sorry about that. And so I'll do the same here. Remember, g prime of y was 0. And then if I do the same thing like I did above, I would get 0 times g of y for x would be 0 squared times y. 0 times y is literally just 0. And so I'd get y cubed minus 0 plus, we have the same boundaries that we did before, and our partial of f of x with respect to y was just a lonely x squared dx. So now that we have our f prime of y, we literally just have to evaluate this. So I'm going to clean it up here. So we have y cubed plus 0 to y x squared dx. So I'm going to evaluate the integral. I'd have y cubed. Using the power rule, we would get x cubed over 3. And we're evaluating from 0 to y. If I plug all of this in, y cubed plus y cubed over 3. And then I'm just going to put plus 0 here, because if I plug 0 in for x, we would just get 0 over 3. So basically, our answer, if I put it all together, I would end up getting that f prime of y is equal to 4/3 y cubed. So that is the final answer. Zoom out a bit. So just going over it again. Basically the process, pick out your functions, differentiate them with respect to the correct variable, plug it into our formula, and evaluate the integral. That's pretty straightforward, just a good review of differentiation, and hope it was helpful. If you need to go back and rewatch, I would suggest doing that. If you want to stay on with me for the next section, another segment of this video will pop up. Okay, so thank you guys so much.